the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is yet another video on orthogonal sets for students in linear algebra. In this specific video, we're going to talk about orthogonal bases, which is very, very important because you would love to have basis vectors that are all totally orthogonal to one another. We're not going to force basis vectors to become orthogonal to each other. Instead, we're going to learn how to write a given vector in terms of orthogonal basis vectors. Creating an orthogonal basis actually comes next. But first, you have to learn how to write a vector in terms of a given orthogonal basis. That being said, let's go ahead and define what an orthogonal basis is. And it's exactly what you probably think it should be. An orthogonal basis for a subspace W of Rn is a basis for W that is also an orthogonal set. It's just basically a basis of orthogonal vectors. If each vector in the set also happens to have a norm of 1, then we call the set an orthonormal basis for the subspace. Again, that would be like the standard basis for R squared or R cubed, because the standard basis is orthogonal and they're all unit vectors, right? In R squared, it's 1, 0, and 0, 1. Both of those are orthogonal to one another and they're unit vectors. But what happens if somebody says, hey, I've got a vector and I have an orthogonal basis for my space. Could you please write my vector in terms of those orthogonal basis vectors? How do you get that done? Well, that's where this theorem comes into play. Suppose we're given an orthogonal basis U1 through UP for your subspace W, which is a subspace of Rn. Then, for each vector in your subspace, you can create a linear combination of those orthogonal basis vectors, and your linear combination is C1 U1 plus C2 U2 all the way to CP UP, but you don't know what those weights are. You know what the vectors U1 through UP are. They are the orthogonal basis vectors. But how the heck are you going to find C1, C2, C3 all the way to CP, those weights? Well, turns out those weights are given by this very complex looking formula, which is going to be very, very important as we move forward. You're not going to forget this formula, I promise you. It is a formula that you use over and over again from this point forward. So the coefficient of the jth orthogonal basis vector, which is C sub j, that's the coefficient of it, can be found by taking the vector that you're interested in, the one that you want to write in terms of the orthogonal basis vectors, dotting it with the orthogonal basis vector u sub j, dividing that by u sub j dotted with itself, which is, by the way, the norm of u sub j squared. And I promise you, that will be the jth coefficient of that expansion or that linear combination. So if you really want to be ugly about this, you could say that the expansion of y in terms of those basis vectors is this ugliness right here. Notice each of the coefficients matches the formula I wrote right here, and they're each attached to the corresponding basis vector u1, u2, and up. Now, something this complex seems like it would take forever to prove, but it actually does not. We'll start by letting U1 through UP be an orthogonal basis for a subspace W of Rn. And of course, because it's an orthogonal basis, we happen to know each of those vectors is orthogonal to one another. That is, U sub I dotted with U sub j is 0, and U sub I is non-zero. Again, that's for all I not equal to j. Well, then let's look at just y dotted with U sub 1. You might wonder why I'm saying that, but it's kind of the same argument I did in the last video, where I'm using just u sub 1 as an example here. Without loss of generality, let's focus in on u sub 1. So y dotted with u sub 1, well, we know that y can be written as a linear combination of those basis vectors. We just don't know what C1 all the way to CP are. But we know that y dotted with u1 is that linear combination dotted with, well, u1. Using distribution, we get to here, and by the way, just like I said in the last video, I'm missing a plus sign there. Somewhat of an annoyance, but oh well. And just like I said in the last video, in fact, each of these dot products is going to turn off. So u1 dotted with up right here, well, because those two vectors are orthogonal to each other, that will become 0. And that claim is true for all the dot products in this linear combination, except for the one dot product where the indices are the same. So in this case, u1 dotted with u1. That is the survivor. So therefore, y dotted with u sub 1 will be c sub 1 times u1 dotted with u1. Now again, just by the same argument I made in the last video, that all of these vectors in this orthogonal basis are non-zero, then u1 dotted with u1 is non-zero. In fact, it's positive. So that's what I'm saying here. Since u sub 1 or u sub I is non-zero for all I, then we can divide both sides of this equation that I'm circling up right there. You can divide both sides of it by the dot product u1 dotted with u1. And now you have what the coefficient c sub 1 is. It's y dotted with u1 divided by u1 dotted with u1. And by the way, for those of you who really just love algebra and think everything follows algebraic laws, I'm going to disabuse you of something right now. You cannot do this. You can't cancel u1s across dot products. That does not work. So please never do that. Anyhow, a similar argument shows the same pattern holds for all I. Sorry, I guess I have a few typos in my lecture notes. I'm fixing them as I'm lecturing. But there we go. So had I started this argument with u sub 2 instead of u sub 1 dotting against y, in the end, I would have gotten that c sub 2 would equal y dotted with u sub 2 divided by u sub 2 dotted with u sub 2. Let's show that this set of vectors v1 through v3 is an orthogonal basis for r cubed. Well, to be a basis, they need to be linearly independent and they need to span r cubed. Well, there are 3 vectors, so all we need is for them to be linearly independent. However, if we can just showcase that they're orthogonal to each other, they're automatically linearly independent and they form a basis for r cubed. So let's go ahead and do that first, and then I'll go back to the second sentence there. All right, so we've shown that v1, v2, and v3 form an orthogonal set, therefore they form a basis for r cubed. And I was somewhat rigorous there. So we have that set of vectors v1, v2, v3. They form an orthogonal set of non-zero vectors, which implies they form a basis for r cubed. Now let's see what the second part of this asks us to do. Okay, we're supposed to express x as a linear combination of the orthogonal basis vectors. Well, that's going to be our newly found skill. We have these orthogonal basis vectors. We know that we can write any vector in r cubed as a linear combination of these basis vectors. We just want to know what those weights are. And by the way, this is solving a system of equations, but we're doing it without solving a system of equations, right? Because if I wrote this in a way that's more familiar to you, I could say, well, what is the solution to that equation? Well, it's the weights, C1, C2, and C3. So we're finding the solution without actually plugging it into an augmented matrix or doing any other little tricky things like Cramer's rule or something like that. Instead, we're using a simple formula that gives us the coefficients immediately because we know our basis vectors are orthogonal. So probably the best way to do this the first time is to just write out all the math off to the right-hand side. So our first coefficient is going to be the vector that we're working with, x, dotted with v1, divided by the magnitude of v1 squared, or in other words, just v1 dotted with itself. It doesn't really matter, it's the same thing. You could do it whichever way, but I'm just going to go ahead and treat everything as dot products here. So x dotted with v1 will be a negative 14 plus 0 plus 20, which is 6. And v1 dotted with itself is 4 plus 1 plus 1, which is 6. Now, I just again want to convince you of how awesome this is. The fact that we have an orthogonal basis allows us to use a formula very quickly to find out what the solution to our system is. Again, this is a system. You may not believe it, but it totally is. If you put these vectors, these orthogonal vectors, in the columns of a matrix, and you put those weights as the entries of a vector multiplying that matrix, and you were to ask yourself, how's that matrix times that vector going to equal the right-hand side, what's it, -7, 0, 20? That's the same thing as solving AX equals B. But instead of doing row operations, we get to use a trick. And it is a trick because it only works if you have an orthogonal basis, which is probably why you could imagine we'd want to get all of our bases to be orthogonal. All right, let's get back to what we were doing. C sub 2. Well, it's our vector x dotted with v sub 2 divided by v sub 2 dotted with itself. Well, x dotted with v sub 2 is 0 plus 0 plus 100. V sub 2 dotted with itself is 0 plus 25 plus 25, which is 50. And we now have the second component of our solution. Finally, C sub 3 is x dotted with v sub 3 divided by v sub 3 dotted with itself. Well, let's see, x dotted with v sub 3, that's going to be 21 plus 0 plus 60, that's 81. And v sub 3 dotted with itself, that's 9 plus 9 plus 9, that's 27. That's going to be 3. So again, we want to express x as a linear combination of the orthogonal basis vectors. C1 will be 1, C2 will be 2, and C3 will be 3. Again, if we were to solve a system that way, we would say the solution to the system is 1, 2, 3. And I spent an exceedingly long amount of time slowly going through this, but the reality is, if all of your basis vectors were orthogonal, man, oh man, this is fast. Not only that, but what if, I'm just gonna showcase something we're gonna run into in the next video, or maybe not the next video, but the video after the next. Oh, it might be the next video actually. But what if, just for giggles here, what if these vectors that form our orthogonal basis, they're orthogonal because their dot products are 0, what if they were, instead of this, what if they were normalized? That is, what if they all had unit length? Well, if you say, man, that's going to involve fractions, that's going to suck, I dislike that, whatever, I would say, well, I dislike fractions too, I totally get it. However, these denominators, which are the magnitudes of those basis vectors squared, well, if they're all unit vectors, the magnitudes are 1. And so if our vectors were not only orthogonal, but normal vectors, that is, they're normalized, they're unit vectors, then your solutions are as simple as that. Now, I don't want you to think that that's what we have right now, because our vectors are not orthonormal, they are orthogonal. So I'm throwing those vectors back in there, those dot products back in there, because we need them when our vectors are orthogonal, not orthonormal. But this showcases where we're heading with the future of linear algebra. We are creating or inventing new techniques to solve large systems quickly, or maybe to approximate solutions of large systems very quickly with a little amount of error. Anyhow, we're done with this video. I know it was short, but I'm trying my best to break these into smaller snippets for you, and I hope to see you in the next video. Be a wonderful human being and have a great day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.